Hello, I'm still studying section 1 here, 18th of January 2025. I didn't like the proof of proposition 10 because they use or refer to a theorem which I think is obviously equivalent to proposition 10, so I would like to prove it directly and I think I've found a way, so I'll just show that. We take a matrix here, and when we operate from the left or from the right with gamma, the greatest common denominator of all the entries will remain the same. That's easy to see, and that means that we can always take the greatest common divisor out. Oh, they don't say that. Well, so that when we multiply through it, then we get n1 here in all entries. So we'll just assume that the greatest common divisor is unity. The first step of my proof is to construct the greatest common divisor of A and B. So we choose H and K. Then we get A times K plus B times A times H plus B times K, which gives the common denominator in the first place. And then we finish it. Oh, that can be done explicitly. This is A divided by the common denominator of A and B, and this is minus B. So that the determinant becomes 1. And then we multiply it. And the next gives minus AB plus AB divided by the common plus minus AB plus minus AB, that gives naught. And then HK plus CD, HC plus KD. And then, since this is naught, the let's call the determinant for n. This must be the determinant divided by the common divisor. When we do it, we get AD minus BC, that's the determinant, divided by the common divisor. So that was step 1. The next is to get a unity up there, and that's slightly different. Or that's more difficult. I don't exactly know how difficult it is to do this because I had a cold while I was doing it. The brain was generally in off mode, so I worked a little on it without finding a way. As soon as I got well, I could piece it together. Well, my procedure is to take each prime out of this one at a time. There may be a smarter way, but that's what I do. So let's say P be the greatest common divisor of A and B. If this prime is not in there, then we can subtract it or make the greatest common divisor of these two, and then it will be smaller than this and not contain p. If p divides this, then we know that p doesn't divide this. And then we can just add it to it, and then we will have a number that doesn't divide, that p doesn't divide. And we know that all row and column operations can be done by gamma from the left and right. So let's assume that p doesn't divide this, and then we must find the greatest common denominator here. So let's just rename it. And we went from the right, so I believe we must do it from the left now. Yes. So now we choose H and K. So that it gives the greatest common denominator, divisor of A, B, and C mark. I don't think it's, it was relevant here that this gives naught, because then when we add this row to this row, this is conserved. So it was actually important that that gave naught. So up here we have H times AB plus. Now there's something very wrong here. We need to put K up here. So let's try again. H times plus K, that gives so now we get the right thing. H times this gives the common denominator, the common divisor. K d mark. A, B, C marks, and they cancel, so now we get a naught here. And then of course we must get n divided by the common divisor. Yeah. So you see now that we have actually we've managed to remove p from this number. And now we must do the same. Take the next prime and remove it. And here we had naught up here. Now we have naught down here, so we need to multiply from the opposite side than the other way here. But generally we can remove all the primes, so we end up with plus minus unity, and can multiply by minus 1, of course. So we end up with 1.n. And then we have something up here. And that's very easy, not necessarily anything there. And then we make row or column operation that way and row operation that way. And then we can make that vanish. I'll just do it with 1. So it's let this be plus, this minus, this plus, and this naught. Ah, that was wrong. That's the second row. That must be minus b double mark unity. So we just extend it like this. So it's still 1 naught c double mark, and then something complicated. And then we do the same thing from the other side to remove c. And like c double mark is conserved, so will naught be. So we end up with a matrix of the form 1n naught naught. If you want to make a more elegant proof, then you can just show that if you have naught in either of these two places, or you can start how you can remove and then assume that A is the least possible one, and then if it's larger than 1, you can show that it can be decreased. That's a more elegant proof, but I like my way better because that gives a procedure for a finite procedure for finding the matrix, actually constructing it, whereby you also construct the two matrices you need to multiply by. So that was my first comment to section 3. This is just a slight comment to the proof, which I find this formulation. It's easy to see that there exists u and v relatively prime, such that where a and b may be any integers really. That's actually, I think it's overcomplicating. What about choosing? Oh, it should be C here, shouldn't it? Well, as far as I remember, it should be C. So if we choose U equals C divided by the greatest common divisor of A and C, and V being minus A divided by the same guy, then U and V are mutually prime, and of course this sum gives naught, and the proof will work with this choice. So I think this is overcomplicating stuff. Hello, February 11th. I have a handyman working on my bathroom, so there will be some background noise, so I hope it doesn't bother you. Now, the book led me to believe that T-P's would give the null operator, or at least that T3 working on a modular form would vanish. And that didn't make any sense to me, so I wanted to write it up explicitly. So we have the right-hand sides by the lemma, and T3 of f is defined by this. And there we have to find the automorphy factors of these guys. They are easy. In the book it shows what to do here, and we factor it from this guy with these two. It's shown on page 208. We need to find the automorphy factors. Here we have -4 on -1, which gives -1, and this unity. So it's epsilon minus 1, which is the imaginary unit, so it's minus I square root minus 4z minus 1. And this is in minus h, so the square root is in the fourth quadrant. Then it's moved to the second quadrant, and this is as well. And this guy is easy. So we compute the product here with the automorphy factors. The first one is trivial, and the next one we have to, first we write this, yeah, and then the minus, and then the square root where we operate with on set with this matrix, giving this, reduce it, and that is what it becomes. Therefore, we have the formula for computing T3, which is not stated in the book. It actually doesn't work. I tried it with k equals 1, where it does work, but in k equals 3 and 5, it doesn't. It simply gives wrong formulas. How could that be? I believe the cause of that would be that this failed, that when we operate with T3 on a modular form, we only get integer powers of q. So of course this guy is invariant under T. So invariance under this generator of gamma 1 level 4 must fail. So I explicitly found out how the right-hand side's right side classes permuted by this guy. So now it's not enough to know that they do, we have to find out how they do it. And then compute the automorphy factor of this and this. And they turned out to have different signs, differ by a minus. And this one is easy because it just gives the fourth root of 3 times square root 4z minus 1. This is the same times, and then the square root of 12 times z third plus 1. So they obviously have the same sign. And here they turn out to differ by sign. I haven't shown you the way of doing it. It's not difficult. So that's my explanation of why T3 isn't a Hegel operator, because it doesn't map mk halves of gamma 1, 4 into itself. Why it should generally fail, I have no idea. What we needed to do next was check, does it work with T9? So again I set n to 4 and wanted just to check that it worked. So we did the same. It's all explained in the book. So I find the automorphy factor as the same as they got in the book. Next, these two guys, they were more involved, and I got minus I and plus I when I, at the end, after comparing with the result on page 209. Now we have the same exercise, but this time with 12 matrices. So the automorphy factor of this, alpha naught g, yeah, giving this, easy. This No, this is actually the guy on the right-hand side. And then on the left-hand side, that was the easy one. Oh, this is trivial as well. So they gave the same sign. And I went through all of them meticulously. And all 12 turned out to give the same sign eventually. That means I have verified when n is 4 and q is 3 squared, then the Hecke operator actually maps the modular forms to a modular form. And that gives some, say when k is 3, it gives some interesting relations between the number of ways a number can be written as the sum of 3 squares, and then 9 times that as well. So I don't know how to prove them or to see directly that these relations hold. They look very weird. I guess it's possible, but I just left it here because now I need to get started on the problems. This section was a very hard study, and I think that the problem is that it hasn't been exposed to teaching before. So I think the section was written very much based on research papers where everything wasn't explained very well. So there's a lot of things I don't understand. But I think I understand it well enough to start the exercises. And then I hope when some of you have taught this material that it will eventually be easier to understand, and the relevant proofs, how to generalize these results, I have no idea. So I hope that the proofs will be relatively easy to follow, but maybe they aren't, I don't know.